In this video, we are going to talk about predicting equilibrium position. But before I start talking about that part, I would like to mention a few important things. So imagine that we have an equation like this, acid and base equation. They react with each other and form the products. This arrow, we call that this single-headed arrow that goes in both direction and equilibrium arrow. So do not confuse this arrow with double-headed arrow, which shows resonance. So the equilibrium arrow means that the reaction, the equation can go in both ways. One way to the product and one way to the reactant. Or we can say means reaction is reversible. Now sometimes the equilibrium prefer one side of the reaction, so it can be the product side or the reactant side. If I draw the arrow in this way, that means products are favored. Equilibrium produces the products more. And if I draw the arrow in this way, that means the reactants or starting materials are favored. There are two ways that we can determine which side of the equation or the equilibrium is favored. The first way that we already talked about a little bit is by looking at the pKa values for the acids in both sides of the equation. And as you remember, equation always favors formation of the weaker acid or higher pKa. So we need to compare the pKa of acid and conjugate acid, and equilibrium always favors the weaker acid. So if you look at this equation, okay. So we have an acid and base reaction. Water is deprotonated in this reaction and converted to hydroxide, and carboxylate anion take the proton from water and becomes acetic acid. So this is our base, attacks the acid and pushes the electrons. So the base, after reacting with acid, converted to conjugate acid, and this one is our conjugate base. So what we care about is our conjugate acid pKa and our acid pKa. So the pKa value for the acid, water here, is 15.7, and for conjugate acid we have here is 4.57. So water has the higher pKa, meaning that it is a weaker acid. So equilibrium prefers the starting material more. The second way is to compare the stability of the bases for both sides of the equation and see which base is more stable. An equation always favors formation of the more stable base. So equation So this is the place that we can use our knowledge that we earned while talking about Oreo. So this is the place that you need to use Oreo to see which base is more stable. Now let's look at this example. Okay. So this is an acid and base reaction. Phenol reacts with hydroxide and forms the products. So the hydroxide is our base because it takes the proton, it's protonated to form the water, and phenol is deprotonated to form the phenoxide. So this is our base here, which attacks this hydrogen and pushes these electrons. So this is our base, and phenoxide is our conjugate base. Now we want to know between these two bases which one is more stable. Okay, so then we need to use Oreo. So if you look at atom, in both of them the negative charge is on oxygen. So atom is not a good factor to use here. Now if you look at resonance, the phenoxide anion can do resonance. If I draw the resonance structure for that, it can do the resonance. Okay, so this is one of the resonance structures for phenoxide anion. You can draw more resonance structure for that, but it's not needed here. The point here is that phenoxide can do resonance, but hydroxide cannot. So this anion is more stable. When phenoxide is more stable, that means the equilibrium favors the formation of that. So the equilibrium favors the product side. Alright, more example here. So we have this equation, acid and base equation. We want to know which side of the equation is favored. So we have Our base is here. This is our base that reacts with our acid to form the conjugate base right here. So to use Oreo, we need to compare these two bases. We want to know which base is more stable. So if you look at them, like both of these conjugate bases, the negative charge is on nitrogen in both of them. So that one is not a good factor to look at. Also, both of them can do resonance. Let's draw the resonance structure. So if I draw a resonance structure for this one, this lone pair here, we are gonna have the negative charge on sulfur. And if I draw a resonance structure for the other one, we have the negative charge on oxygen. So in the resonance structure, the negative charge is on oxygen. However, here the negative charge is on sulfur. And now we can look at the atoms. We know that sulfur and oxygen, they are in the same column, same group. However, sulfur is bigger than oxygen, so it can stabilize the negative charge better. Therefore, this base is more stable, meaning that the equation favors the starting material. Another important skill to run organic reactions is to choose a right solvent. Solvent is used in organic reaction in order to dissolve the reactants, so it can facilitate the reaction without participating in the reaction itself. Also, sometimes solvent is used as a source of acid or a base. Majority of the time, we prefer the solvent that we are using in the reaction doesn't interfere in the reaction, and if it does, we cannot use that solvent. So for example, let's look at this example here. We want to know whether ethanol is a suitable solvent for this reaction or not. So for a moment, let's think about it. Now, so something can happen in this reaction. A side reaction can happen if we use ethanol as a solvent. So basically ethanol, which is a protic solvent because it has hydrogen attached to an electronegative oxygen, so it's a protic solvent, can react with this base, amide base, and forms ethoxide and ammonia. So it's an acid and base reaction. Based on the information that we have, using the information that we have and we learned, we need to predict which side of this side reaction is favored, the product side or the reactant side. So what we can do, we can compare the pKa of the acids in both sides. So in this part, we have alcohol. This is our acid. The pKa is 16. And in this part, ammonia, which is an amine, is our acid, which has pKa of 38. So ammonia has the higher pKa, meaning that it is the weaker acid. So the equation prefers formation of the product, which is not very good in this reaction because the amide anion, instead of reacting with this substrate, will react with the solvent and forms these side products instead of producing our favorite product. So what we say is that amide ion is strong enough base to deprotonate the solvent, which is ethanol. And this is not favored. So ethanol is not a good solvent here. Or in another word, we can say that amide is a stronger base than the conjugate base of the solvent. So we cannot use a solvent that has a weaker conjugate base than the base that we are using in the reaction. So ethanol is not a suitable solvent in this reaction. We need to find a better solvent for our purpose. Counter ions, negatively charged ions, our bases, are always accompanied by positively charged species, which we call that cation or counter ion. So the counter ion is basically the positively charged cation for our bases. And so majority of the time, as I said, we don't show counter ions in the reactions because they are not very important in our organic reactions. So for example, if you want to use hydroxide ion, you may see that as a form of potassium hydroxide or sodium hydroxide or lithium hydroxide. So these metals, they are all the counter ion for the hydroxide anion. But what participate in the reaction is the hydroxide anion, not the basically the counter ions. And the counter ions, these metals, are just there to stabilize the negative charge. Now, if you look at the equation in here, if you want to show the full reaction that includes the counter ion, so we have sodium amide react with water to form ammonia and sodium hydroxide. So the sodium cation right here, this is a counter ion in the reaction. But oftentimes we don't include the counter ions in the reaction. So this reaction can be written as amide anion reacts with water to form ammonia and hydroxide anion. So we just omit the counter ion, but we know that these ions, they have a counter ion next to them to stabilize their negative charges. Lewis acids and bases, this is the last topic for chapter 3. The definition of Lewis acids and bases is broader than Bronsted and Lowry definition. So a Lewis acid is a molecule that can accept electrons, or we can even say it has empty orbital, so it has a space to accept the electrons, or we can say it doesn't have full octet. And a Lewis base is a molecule that can donate a pair of electrons. So if you look at the reaction below, if you want to consider the Bronsted and Lowry definition here, hydrochloric acid donates the proton, so this is our acid here based on Bronsted and Lowry definition, and water takes the proton, so it is our base. Now, if you look at the base takes its lone pair to attack the proton. So basically, the base donates the electrons. So based on Lewis acid and base definition, water is also our Lewis base, and proton accepts the lone pair of electrons. So you remember we talked about proton. Proton is a hydrogen without a lone pair, and hydrogen without a lone pair has an empty orbital. So it is our Lewis acid. But sometimes we cannot use Bronsted and Lowry definition. So if you look at this example here, if you look at the arrow, the lone pair of electrons on oxygen goes to the empty orbital on boron. So water donates the electrons, meaning that water is our Lewis base. Now boron can accept a pair of electrons, so it is our Lewis acid. So we know that boron doesn't have the octet, it doesn't follow the octet rule, but that doesn't mean it cannot accept electrons. So boron has an empty orbital, it has enough room to accept a pair of electrons. But if you want to use Bronsted and Lowry definition here, it's impossible because there is no hydrogen attached to boron, so we cannot use that definition. Another important thing, when we have Lewis base reacting with Lewis acid, we show the movement of electrons with only one arrow. So for Bronsted and Lowry acid and base reaction, we use two arrows, if you remember. But here we only use one arrow to show the movement of electrons. Now if you look at the product, so in the product there is a bond between oxygen and boron right here. Now oxygen has 3 bonds and a lone pair, it is positively charged. We can calculate the formal charge on boron. So as a practice, boron is in group 3, 3 valence electrons minus number of bonds 4, and minus the number of electrons, which is 0, so equals to -1. Now as a practice, let's look at the example below, draw the mechanism and the product. So think about it for a little bit. Remember, Lewis acid can accept electrons and doesn't have the octet of electrons. So we first draw the lone pairs on oxygen, and then we have a carbocation here. So we know carbocation has only 6 electrons, so it doesn't have full octet. Therefore, it can accept the lone pair of electrons. So let's draw the lone pair of electrons on oxygen. And carbocation, it doesn't have full octet, so it can accept electrons. So to show the mechanism, I use an arrow that attack the acid. So the base attacks the acid here. Now to draw the product, remember oxygen, the hydrogen attached to it. This is the new bond, this bond right here. This is our new bond. And then we have our molecule. So just number these carbons. Doesn't matter which is 1, which is 2, 3. Just want to show you, hopefully you can track what's happening. Now in the product, don't forget oxygen has a lone pair and 3 bonds, so it is positively charged.